Hi, welcome to another video on control systems. In this, we will focus on root locus of a system, and hence we comment on the stability of the system. Excuse me. Before we proceed, so you should know what is transfer function of a system, poles and zeros of a system, characteristic equation, and how to write the roots of a given characteristic equation. Okay, with these prerequisites, let us move on to root locus. uh, Before we actually proceed with the actual control system, so let us have a look at this word root locus. So there are actually it is formed out of two words. One is root, other is locus. Here roots, okay, root nothing but, okay, now we are talking about roots of characteristic equation, roots of characteristic equation. uh, this is what we are looking at. So we are looking at roots of the characteristic equation, and locus, as we know that it is joining of various points, is nothing but locus. So this is locus. So what is these points we are talking about? We are talking about the roots. It is the joining of different roots is nothing but root locus. So it is like joining the roots of the characteristic equation. How it goes is actually the root locus. So locus of roots is nothing but root locus. So we know that. So now let us concentrate on roots of this del f s. Why this root locus is important for control systems? So let us explore, okay, why it is so. We know that this is a typical closed loop transfer function with negative feedback, with GFS as a forward block and HFS as a feedback path gain. We know that we can write the open loop transfer function is nothing but open loop transfer function is GFS into HFS. You open the loop, find out what is this till here, what is the transfer function. It is GFS into HFS. We also know what is closed loop transfer function, which is nothing but CFS by RFS, which can be written as GFS by 1 plus GFS into HFS for a negative feedback. And let us try to find out what is characteristic equation. Characteristic equation, we know that it is represented as del of s, and it is nothing but 1 plus GFS into HFS equating to 0. So we know that this is the denominator of your closed loop transfer function. We know that in a transfer function, denominators will indicate the poles. Since it's a closed loop transfer function, so this denominator will indicate the poles of this closed loop transfer function. So since you are equating the denominator of your closed loop transfer function to 0, so roots of characteristic equation are nothing but closed loop closed loop closed loop poles. That is, what are roots of this characteristic equation happens to be the closed loop poles. So why these closed loop poles are important now? So we know that for a system, when the system is okay, when the system loop is closed, you will end up with this is RFS and this is CFS. So this is your transfer function. This is your transfer function. So once you know the closed loop poles, you can comment on the stability of the system, whether the poles in on S plane, where the poles are the poles are on left hand side of the S plane, or is it on the right hand side of the S plane, or it on the imaginary axis. So we know that, so if the closed loop poles lie onto the left hand side, the system is stable. We know that if the closed loop poles are lying on the right hand side, then it is unstable. If the closed loop poles lie on the imaginary axis, then it is oscillating. So the location of closed loop poles matters a lot in deciding the stability of the system. Stability of the system. We also know that usually this characteristic equation, suppose if I consider GFS into HFS for a unity feedback system is K into S plus 3 into some S plus 6. I can write del of S of this, which is nothing but S plus 3 into S plus 6 plus K equal to 0. So in this equation, you can clearly notice that, so there is a K value which we call it as root locus gain. So this is a gain parameter. The K value can vary from 0 to infinity. Thus is it should be greater than 0 but it should be less than infinity. So this is the range of K. So naturally if you can see, if the value of K changes, the closed loop pole position will change. So we are interested in how does, again I'll repeat, as the value of K changes from greater than 0 to less than infinity, the roots of this will change. The roots of this is nothing but closed loop poles. That will tell you whether the poles are there on if the poles are there on left hand side it is stable, if the poles are there on right hand side it is stable. So it's very interesting or important to know, as the value of K changes, where are these closed loop poles, because K will want to tell what is the position of your closed loop pole. Position of closed loop pole will tell me what is the stability of the system. So this K is now related to the stability of the system, which will decide where the poles are. So if we get some clue, how does the closed loop poles move or change their position if the value of K changes, then it's very good. So what does this root locus will do? This root locus will tell us, how does the closed loop poles move as K goes greater than 0 but less than infinity. This is nothing but root locus. Root locus. Root locus is nothing but path traced by closed loop poles as the value of K ranges between greater than 0 to less than infinity. So this is absolutely trying to locate the closed loop pole position as K value increases, because that K value, that closed loop pole position is important for me to know the stability of the system. So we are supposed to know, we are supposed to plot the root locus for a given transfer function for various values of K. So what is required to plot root locus? The requirement is, the requirement is I should know what is GFS into HFS. So let us consider it's a unity feedback system and the feedback is negative feedback. The feedback is negative feedback. With these things in our mind, so what is required is, the requirement to plot the root locus is a transfer function with K as its gain, which is variable. So you can take it as S plus 3 into S plus 6. Suppose you take this as your transfer function. So uh, we know that there are two closed loop poles. Sorry, there are two poles. How many zeros are there? There are no finite zeros. So you know the closed loop. Sorry, you know the open loop transfer function. You know the open loop transfer function. As the value of K increases beyond 0 and less than infinity, I should know where does the closed loop poles move. So let me start writing the root locus. Set me right writing the root locus. So root locus is now, it's again on S plane. This is on S plane. So this is your real axis. This is your imaginary axis. Since the pole is, this is open loop pole at -3 and -6. So first and foremost thing is that root loci. How many root loci are there? Number of root loci is equal to number of poles. This is a root locus. You're plotting a root locus. You're plotting a root locus. In that root locus, you may have so many number of root loci. Number of root loci is equal to number of poles. So here there are two poles. So number of root loci is equal to 2. Second one is, where does root loci start? Where does the root loci start? Because we know that as the value of k ranges from 0 to infinity, the closed loop poles will start moving. But which is the starting point? Root loci starts from the open loop loop open loop pole position. So what is the open loop pole position of this particular thing? So open loop poles are there in at -3 and -6 when the loop is open. So it will start from -3 and -6. It will, of course, we know that there are two root loci, and the starting point is the open loop pole position, which is at -3 and -6. So this is the starting point of root loci. Next is, where does a root loci will end, or where it will terminate? Where it will terminate, we know that all root loci will terminate at infinity or at finite 0. Now in this particular transfer function there are no zeros, so that's why both the root loci will terminate at infinity, because there is no finite 0. Suppose if you had a 0 here, then one of the loci would have gone to that particular 0 position. Now we are now done with how many root loci you want to have. How many? Two root loci. The starting point of root loci is nothing but -3 and -6, and we have the termination point is either infinity or at finite 0. Since I don't have any finite 0, both will terminate at infinity. Then now we know that root loci will start from here. Next very important point is, where does the root loci exist? So does the root loci exist here? Does the root loci exist here? Does the root loci exist here? Now next fourth point is existence, or which uh, which part of a real axis of your S plane is a part of root locus. This is very important, the starting point. This is your S plane real axis. In this, maybe what you can do is you can just divide this into, you can write some imaginary lines here. So I can say, from here to the right of it, there is a segment 1. Between these two lines, let me say it is segment 2, and towards the right of it is segment 3. I have three segments, S1, S2, S3. Now I want to know whether this segment is a part of root locus, whether segment S2 is a part of root locus, whether segment S3 is a part of root locus. To know that, there is a rule, or there is a what method to know the which part of the real axis of S plane is a part of root locus. So what you can do is, you can simply stand here. So before you stand, you made this partition of the entire S plane, depending on where the open loop poles or zeros are there on the S plane. So this is one partition, this is other partition. I am standing here. I look towards the right. I will look towards the right. How many poles plus zeros are there? There are no poles and zeros. So there are no poles and zeros to the right of it. If there are no poles and zeros, then this is not a part of root locus. Because the whole idea of partitioning this is to know whether this segment 1 is a part of root locus, whether segment 2 is a part of root locus, whether segment 3 is a part of root locus. Now for that, you just, okay, because this is your entire S1 segment, you stand anywhere here. So you stand anywhere here and look towards the right. So you're looking towards the right. How many poles and zeros are there? Nothing. So that's why this is not a part of root locus. Then you stand here. So you literally stand here, look towards the right. So how many poles plus zeros are there? You have one here. So since you have one towards the right of this scene, so you're seeing towards the right. So there is one, meaning this is this portion is a part of root locus. You darken this line. You can see I'm darkening that. Here I didn't dark because this is not a part of root locus. So now this is not a part of root locus. This is a part of root locus because you stand here, you stood here and then look towards the right. There was one one pole to the right of this observation. Next, you stand here. Again, look towards the right. How many poles and zeros are there? It is 1 plus 1, 2. So it is even in number. If it is even in number, then this is not a part of root locus. So you're just simply writing this is not a part of root locus. You're not darkening that. You can see you darken this. You didn't darken this, you didn't darken. Why you didn't darken this? Because there are no zeros and poles. Here there are odd number which is 1. Here it is even number. So here it doesn't exist. Here it doesn't exist. Only segment 2 is a part of root locus. So this is very important while plotting the root locus of any given system. So we identified where does the root locus exist on the real axis. Next important point is, first it is a very easy one, the direction of root locus. Okay, these points are very trivial, so maybe for initially 2-3 plots you may have to just carefully do it, otherwise you can just then you can easily do all these points. Direction of root locus. We know that root locus exists here. So root locus will always leave, it will leave the open loop pole as k goes greater than 0, meaning this is the existence. So I have to write the arrow mark like this. So this is leaving the pole, this is leaving the pole. You can see now the arrow mark is this way, so this is actually going like this. So actually the poles leave this. So now this is as the value of k increases, the closed loop pole which was there at -6 has gone to -3 and -6 will start moving towards this is moving towards right side, whereas this is moving towards left side, because this is how they are moving. Next, once they are coming like this, they will meet somewhere. So that is what is next important. So when they meet, they break there. So next important point is breakaway point. So let me write the sixth one is break away point. Breakaway point. So to, because we know that, so there is a value of k0 here, k0, as you keep increasing the value of k, so this is for a bit greater value of k, it is coming here, this is also coming here. For a particular value of k, both the roots will meet each other, so they will be overlapping, they will be meeting at each other. We call it as breakaway point. We can find this breakaway point by taking the derivative of k with respect to s and equating it to 0. If you do this dk by ds, then we will get the value of s where both both poles both poles which are coming in the opposite direction, both poles coming in opposite direction meet. That is nothing but where they break, where they break. So now they break away point. Once they break, they will actually become complex, because once the poles are there in real axis on this plane, they are real axis. Now when they break, they will become complex. You can see it is becoming complex here. So breakaway point. So for that I need to know what is k value. So from this, can I write what is del of s? So what is del of s for this? So del of s for this is s plus 3 into s plus 6 plus k. How do you write del of s? Is it's actually 1 plus gfs into hfs equal to 0. It is now 1 plus k into s plus 3 and s plus 6. Take the LCM. It is s plus 3 into s plus 6 plus k divided by s plus 3 into s plus 6 equal to 0. When you are equating these to 0, you will get this as your characteristic equation. This is your characteristic equation. So can I write now del of s is equal to s square plus 9s plus 18 plus k is equal to 0. So then can I write k is equal to minus of s square plus 9s plus 18 is my k value. So now can I write what is dk by ds? So differentiation of this is now 2s plus this is 2s, this is 9 plus 0 equal to 0, because you are equating this dk by ds to 0. So then what you have? You have 2s plus 9 is equal to 0. Then s is equal to minus 9 by 2, which is minus 4, minus 4.5. Meaning, what does this mean? As I said here, it will give the value of s at which both poles come in opposite, both poles coming in opposite direction will meet. Meaning that is the breaker point. So breakaway point is happening at minus 4.5. And we know that where does these root loci will go? They will go to infinity, because there are no finite zeros. Since they want to go to infinity, there should be some one who is guiding them to go to infinity. So that is nothing but asymptotes. So asymptotes are the ones which will guide the root loci to go to infinity. So let me write what is asymptotes. What is this asymptotes? This asymptotes is nothing but these are these are the straight lines which which will which will guide the loci to go to infinity. Asymptotes are nothing but these are they are straight lines which will guide the loci, okay, root loci to go to infinity. So then comes how many, what is the number, what is the number of asymptotes, how many asymptotes are required? It is always nothing but how many number of loci will go to infinity, those many asymptotes you want. Generally it is p minus z, where p is number of poles, z is number of zeros. So number of asymptotes are p minus z. In this particular case, you have two poles, there are no zeros, so there are two asymptotes required. There are two straight lines required. So that is first thing. Next is, where does asymptotes meet? Where does asymptotes 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 meet? Which is nothing but centroid. This centroid is nothing but summation of all real part of open loop poles minus summation of all real part of zeros divided by p minus z. Now it is summation of all real part of open loop poles, pole position, and all real part of zero positions. So what is that we have? We have poles at minus 3, minus 6. This is a summation and I don't have any zero there, by 2. So is it not minus 9 by 2, which is nothing but minus 4.5? What is this minus 4.5? Minus 4.5 is where these two asymptotes meet. These two asymptotes meet. Okay, where does asymptotes meet is, since you know that there are two asymptotes, the two asymptotes will meet at minus 4.5. Next important point is angle of asymptotes. Angle of asymptotes. Asymptotes. This angle of asymptotes is always common. If we have one asymptote, then it is lying at 180 degree. If we have two asymptotes, then one of the asymptote is at 90 degree, other one is at 270 degree. If we have three asymptotes, then one asymptote is at 660 degree, other is at 180 degree, other is at 300 degree. If you have four asymptotes, then it is at 45 degree, 135 degree, 225 degree, and 315 degrees. So these are the angles of asymptotes always. If you have one asymptote 180, if you have two it is 90, 270, if you have three it is this, if you have four it is this. Now in this case, okay, we'll just come to all these things in the coming problem. In this case, how many asymptotes you have? Two. So then the angles are 90 and 270. So this is what we have. So we have this as our, okay, we have this here. So let us take that is, so we started with, one second. So that is second one, then this is the third one, and this is our asymptotes, the fourth one. So now let us look at fifth. What is fifth now? So before we go to fifth, we can actually write it here itself. So now this is our pole position, then this is how it went, and then let me write, this is at 4.5 you have asymptote. One of the asymptote is at angle 90 degree. You can see this is the reference angle. From here you measure the angle, it is 90 degree, and one more one is exactly beneath that. If you actually measure this angle from here to here, it is actually 270 degree. So this is what is 270 degree, this is what is named. So this is asymptote number 1, this is asymptote number 2. So these two are the references how it goes. Now what is the role of this asymptote? The role of the asymptote is to guide the root losses to go to infinity. We know that pole is leaving this minus 6, pole is leaving this minus 3, it's going in this direction, they break at minus 4.5 and they will become complex, and there is a asymptote waiting it to take it to infinity. It actually goes like this. Here it's going here, see the direction, it's actually keep going, it's actually keep going. As the value of k increases, this is moving here, this is moving here, and at s is equal to minus 4.5 they'll meet each other. If the value of k further increases, then it goes here. You can actually find the value of k at this point. So you have this k, no? What is the k expression? You have the expression of k as this. Somewhere you had it. Where is the third? Okay, this is k. So now in this, if you substitute s as minus 4.5, I will get the value of k at this point. So shall I do that? I can do it here. So it is now minus 4.5 square plus minus 4.5 into, maybe let me just put a parenthesis, minus 4.5 into 9 plus 18. So this whole minus into minus 1. You can see the value of k at this point is 42.75, meaning as the value of k increases beyond 0, when it is 0.1, 0.2, 1, 2, 3, 4, 5, 6, 7, 8, when k is 42.5, both the poles are there here. If the value of k is going beyond 42.5, 42.75, then the poles will become complex. Suppose if the value of k is 1000, the poles are here. If the value of k is 2000, sorry, they are here, they are here, they are here. They just keep moving. This is how the closed loop poles will move as the value of k increases. If it is 0, they are here. If you increase the value of k, it comes here. When k is 42.5, it will be there at minus 4.5. More than 42.75, then the poles will become complex. This is how you have to plot the root locus. Let me again recap it. The requirement is open loop transfunction, locate the poles and zeros, and if zeros are there, locate it. Then try to identify the number of loci. It's always equal to number of poles. And root loci starts from open loop pole position. The root loci will end at infinity or 0, depending on whether zeros are there or not. Then identifying which part of the root locus a part of root locus is important. So that's what you are trying to identify by making this into n number of segments, by writing lines at the open loop pole and zero position. You would be able to find three locations or three segments and identify S2 as a segment where the root locus exists. You darken that portion, and then you actually wrote the direction of root locus, so it is leaving the pole. And then you, because you know that two loci will go to infinity, we need to have asymptotes. So number of asymptotes we found, it's always equal to p minus z as the number of loci will go to infinity, those many asymptotes you want. Then you want to have where does asymptotes meet, which is nothing but real part of poles minus real part of zeros by p minus z, which is happens to be minus 4.5. Then the angle of asymptotes, this what is these standard angles, and then we actually plotted the final root locus. Now what is the outcome of this? As the value of k goes from 0 to infinity, the poles are taking this position. So this is a locus formed by the roots of the characteristic equation. So if you can see here, if this is your S plane, so this is your imaginary axis, this is your imaginary axis, the poles are always onto the left hand side of the S plane. So for any value of k between 0 and infinity, roots are always onto the left hand side of the S plane. So system is stable. System is stable. It's not simply stable, it is absolutely stable. Absolutely stable. Because this can never go to right hand side. The roots will never go to right hand side of the for any values of k, even up to infinity. Uh, this is what is root locus is. So in the next video we'll just do a bit slightly improvised root locus and then try to understand its locus.